This is Algebra 2, Unit 4, Lesson 14 on Newton's Law of Cooling. The temperature of a cooling liquid in a large room with a steady temperature is a great example of a type of transformed exponential function. We'll explore this today to see how a simple exponential function can be used to build a more complex one. Alright, so let's consider the simple decreasing exponential function f of x equals 8 times 1/2 to the x. So we could use our calculator to sketch the graph using the window indicated. Okay, now first of all, we should be able to predict what this graph is doing. What's my y-intercept of this graph? Well, according to that, it should be at 8. That's the y-intercept. And is this function increasing or decreasing? It's decreasing because the multiplier is less than 1, or the growth factor is less than 1. So it's decreasing. Okay, so we should know what it looks like. My y-intercept is going to be at 8. Let's see if we get that. So y equals 8 times 1/2 to the x raised to the x. Okay, and I want to set my window. My x's were from 0 to 5. 0 to 5. And my y's were from 0 to 10. 0 to 10. Okay, so if I hit my graph key, let me see. 1, 2, 3, 4, 5, 6, 7, 8 is my y-intercept. It is decreasing. And 1, 2, 3, 4, 5, it gets down here at the other end. So it looks kind of like this. It starts 8 and it goes down like that. Okay, so clearly the y gets smaller as x gets larger. Does it ever equal 0? Will this line ever equal 0? No. Why will it never equal 0? Well, think about this. Every time we are multiplying by 1/2, we are taking 1/2 away. So it gets very close to 0. But since we're multiplying by 1/2, there is always 1/2 remaining. So it'll get microscopically close to 0, but it'll never actually get there because there's always 1/2 remaining of what you started with. If you're taking 1/2 of something, there's always a 1/2 left. Okay, so this is a decreasing exponential function. Okay, so using this basic idea, let's see if we can model liquid's temperature that is cooling in a large room. All right, let's assume a liquid starts at a temperature of 200 degrees Fahrenheit and begins to cool in a room that is at a steady temperature of 70 degrees. All right, so draw a rough sketch of what you believe that the liquid temperature function looks like as time increases. Okay, so starting temperature we said was going to be 200, and it's going to decrease. So we should expect it to decrease down. All right, now what happens when it gets to 70 degrees? Well, the temperature is probably going to level off. The temperature is not going to go down to 0. The temperature is going to go down to 70 degrees because that's the temperature in the room. So if we go down to 70 degrees right here, and let me draw it as a dotted line so we can see what we're doing here. If this is a dotted line like this, would be 70 degrees. Okay, instead of going down to 0, if it's room temperature, it's going to stay at 70 degrees once it gets down there, or get very close to 70 degrees. So this would come down like this over time, and it eventually get very, very close to 70 degrees. Okay, so based on your graph from A and your work in exercise 1, why would an equation of the form y equals ab to the t not model this cooling well, assuming that b is between 0 and 1? And how can we modify the equation to make it model the situation more realistically? Okay. So it is going to modify the equation. It's going to increase from, instead of going from 0, it's going to go up to 70. So this is going to shifts up 70 degrees. So when we have a function model, y equals a, b, raised to the t, and we're shifting up, what does that affect? It affects the y-intercept. Okay, so the y-intercept or excuse me, the y-intercept right here would be 70 instead of 0, so we would add a c here because the liquid is approaching 70 instead of approaching 0. It's not approaching 0 anymore. All right, so it's going to shift up 70 degrees because of the room temperature. So this is going to be the shift up, okay, because that affects the y-intercept out here. Okay, so instead of being down like this, it's going to shift up to 70 degrees. So that's where the C comes in because that's where the shift would be. All right, now let's stick with the same cooling liquid we had before, one that starts at 200 degrees and cools down a room that is held at a constant temperature of 70 degrees. We will now model this cooling Fahrenheit temperature using the equation F of T equals A times B to the T plus C, where A, B, and C are all parameters or constants in the model, and T is time in minutes. Okay, so which of these constants is equal to 70 and why? Think about the last problem. Okay, now we said this is going to be shifted up, so it would be F of T equals A times B to the T plus C. It's going to be the C value. C was equal to 70 because that function is approaching 70 instead of 0. The function approaches 70 instead of 0. All right, so that's going to be a shift up. Okay. All right, so we know C is going to equal 70. So this is what we have for right now. F of T equals A times B to the T plus 70. That's what we have right now. Now, none of these constants is equal to 200, but T of 0 does equal 200 because, remember, this is the starting temperature, is when T is equal to 0. Okay, so we know if it starts at 200 degrees, T equals 0 is the time. Okay, so if we figured out what constant does this let you solve for? All right, let's plug in T equals 0. T equals 0 we know is 200. A, B to the 0 plus 70. Okay, what's B to the 0 equal to? That's equal to 1. So that gives you 200 is equal to A times 1 plus 70. 200 is equal to A plus 70. So what does A equal? A now equals 200 minus 70, which is equal to 130. So we just found A. So by using the starting temperature of 0 at, or excuse me, the time to 0 at 200 degrees, we can plug in and find our value. All right, so we knew C was 70. We figured out A is 130. So let's see what we have for the information that we have. We now have F of T is equal to, we just found A was 130 times B to the T plus 70. Okay, so in order to find the value of B, what additional information would we need? We need one additional point on the graph. All right, so we need one additional point. We need another value of T and F of T. Okay, so determine the value of B if the temperature after 5 minutes is 153. Okay, and round to the nearest hundredth. All right, so we're going to take this formula right here, and we're going to plug in 5 for T and 153. That's my other point. All right, so that gives me 153 is equal to 130 times B raised to the 5th plus 70. All right, and that'll give me what B is. Okay, so let's solve this for B. First thing we do is subtract the 70. All right, 153 minus 70 is 83, is equal to 130 B to the 5th. All right, I want to solve for B, so I'm going to divide by 130. It's 83 divided by 130. And then what do I do with b to the fifth? I take the fifth root. All right, and I'm going to take the fifth root of both sides. I'm going to leave this in fraction form because I'm going to round it anyway. So it's going to be the fifth root of 83 over 130 is equal to the fifth root of b to the fifth. So b is going to equal, I'm going to grab my calculator. All right, the fifth root, if you hit the math key, remember, it's number 5. You just have to put your root in. Your fifth root of 83 divided by 130. 83 divided by 130. You can use the fraction key if you want to, but this is going to be a decimal we need anyway, so that's just fine. All right, and it said round to the nearest hundredth. So this is going to be 0.91. So b is approximately 0.91. All right, so now we have c, we have a, and we have b. So now we can write the whole equation. All right, so now we have all the parameters to be able to write the equation. We would have f of t equals, our starting value, we figured out a was 130. B was our multiplier, is 0.91, raised to the t, plus 70, which was our c. So this is our equation that we have. All right, so what is the temperature of the liquid after half an hour, or 2 hours? All right, now remember what our units are. T is in minutes. T is in minutes, don't forget that. All right, so half an hour would be f of 30. So it's 130 times 0.91 to the 30th plus 70. So we go to our calculator. 130 times 0.91 raised to the, oops, wrong button, raised to the 30th power, and then plus 70. And it will be approximately 77.679 degrees, approximately. 77.691 degrees. So that's after 30 minutes. All right, what would it be after an hour? That would be f of 60. So that would be 130 times 0.91 to the 60th plus 70. All right, now if I go to my calculator, I just have to take this equation and change 30 to 60. So I'm going to go up here and grab that one. I'm going to back up and change 30 to 60. Okay, there I go. And press enter. And now it's at 70.453 approximately. 0.453 degrees. And then after 2 hours would be how many minutes? That would be 120 minutes. 130 times 0.91 to the 1/20th plus 70. All right, so I'm going to grab that one, change to 120. Change this to 120. My exponent, whoops, too far. 120. And press enter. It's now down to 70.002 degrees. 70.002 degrees. Okay, so you can see we just figured out all these values by using our formula. All right, so use your calculator, sketch the graph of the liquid's temperature, and decide on an appropriate window and label your axes. Okay, so what was our maximum temperature? We said the starting value was at least 200, wasn't it? Okay, so we know the temperature is going to be at least 200, so I'm going to make this, say, 250. So we know our starting temperature is going to be 200. Okay, and for the time, sketch the graph on an appropriate window. Let's see, from 0, let's just do an hour for right now. Let's do 0 to 60. Okay, so let's use our graph. 130 times 0.91 raised to the x plus 70. And for our window was from 0 to, let's say, use 60. And then 0 to 250 for our value. And we graph it. And we should look something like that. And you can see it's going to level out down here about 70. Okay. So your graph should look something like this. Whoops. Pretend that's straight. It's going to level out to be approximately 70. All right, we'll finish letter G tomorrow in class.